Hi folks, welcome back to another lesson, and this is part 2 of the Gay-Lussac law, and in this case we're going to look at the experiments for it. It's very similar to the Charles's law lesson, however we are doing a little bit more because we're going to look at something called absolute zero, and you're hopefully going to be able to define and use the term. We're also going to explain how we get this unit kelvins from the experimental data. So a few things you need to remember. We need to remember about a graph which looks like this is a proportional relationship. Secondly, we need to remember that to convert to kelvins, we add 273. And remember that the Gay-Lussac law and the Charles's law are mathematically both the same. And so we can share a lot of the same ideas between the two. So this will make our analysis a little bit quicker. So here's the experiment that you'd be doing, or we'd be doing in class, because it can be quite dangerous. You would have a flask where you put air into it. You would then put this flask, which has a temperature probe inside here and a pressure probe here, and this would be connected to Alba. And then you would put this flask of air into it, into a big beaker with water, and you would gradually heat the water up. So what you're doing is you're heating the air inside by heating the water around it. And then obviously as the temperature increases, we can then measure the change in pressure. Now the key thing to remember about this is that the water must cover the whole of the flask, otherwise you're not heating all of the air. So that's something very important to remember. And again, there is a wee video link to show this experiment taking place for real. Now, here are some of the results we get, and we would plot this into a graph. Can you guess what the shape of the graph is going to look like? And I suspect you didn't think it would look like this. Now, if you look at it, you'll know straight away I've done something silly here because I plotted this in degrees Celsius rather than in kelvins, right? Hopefully you spotted that. Now, if we look at it, we can sort of see it's almost like a proportional relationship, isn't it? Because it's a nice straight line. The only problem is it doesn't go through the origin. So how can we actually make this go through the origin then? Well, remember, for it to be proportional, it's got to go through the origin. So let's see what we can do to fix that problem. So let's draw a wee sketch of this graph, and I would like you to be able to sketch this. So make sure you copy the slide. I'll tell you which bit to copy. So this is our graph as a wee sketch. And what would happen if we kept extending the line back? Well, if we did this, we would get that the line would cross the x-axis at minus 273 degrees Celsius. So I would like you to be able to sketch this graph along with the one for Charles's law. And what you can see here then is, well, if the axis actually started here, that's almost as if we've got a proportional relationship, isn't it? So let's look at how we can fix this then. First of all, we're happy that if we extend the graph back the way we get this crossing the x-axis at minus 273. So we can kind of cheat in a way and say, well, if we don't plot it in degrees Celsius, then we can choose where the origin is. So we could just get rid of the origin there. Okay, and we can just draw it at the end there. And if we do that, you can see we have a really nice straight line going for the origin. Now, the only problem then is that we can't say it's measured in degrees Celsius. We have to come up with a new unit. And there's no reason why we can't do that, because these units here are decided by us. So we put the 0 there to show it's going for the origin. And this is what our new graph would look like. And you can see we label the units kelvins after Lord Kelvin, who discovered this kind of unit. And you can see we now have that lovely straight line going to the origin. So we can now say pressure is proportional to temperature. And that's what the relationship is between the two. Okay, so to summarize everything we've done, we've looked at pressure and temperature, and if we draw a graph of pressure against temperature in degrees Celsius, we see it doesn't cross through the origin. What we can do is we can extend that line until it crosses the x-axis, and then to make it go through the origin, we just relabel our x-axis to be kelvins instead of temperature, and we get our proportional relationship again. And so that's how we get this U unit kelvins. And of course, we've got to remember that we kept the volume of the gas the same. Now, a few things about converting between kelvins and degrees Celsius. First of all, 0 kelvins is called absolute zero. And it's the lowest temperature we can reach because at 0 kelvins, the kinetic energy of the particles is 0 joules. And this is really important because remember, we had a definition for heat and temperature. Heat was how much energy it had. Temperature was the measure of the average kinetic energy of the particles. And literally at 0 kelvins, the average kinetic energy of the particles is 0. So therefore, you can imagine the particles aren't moving. It's a completely new state of matter. And as a result, kelvins can never be negative because you can never get a negative kinetic energy. It doesn't make sense. And so absolute zero is equal to 0 kelvins is equal to minus 273 degrees Celsius. And this is why we always add 273 to get kelvins. So just like the Charles's law, we can write P is proportional to T. And remember, all this means is that if we can rewrite it as P over T is equal to K. And remember, we have to keep volume constant and that temperature has to be in kelvins. Now, we can use this trick again of using P over T equal to K to show that pressure and temperature are proportional even if we don't have the graph. So let's look at an example of this on the next slide. So here's an example where we're given 4 data points for a pressure temperature experiment, and we have to show using all the data that pressure and temperature are proportional. So we write down a relationship. P over T is equal to K. We then plug in each pair of values. So the first one we're going to do is 15.75 divided by 50. Notice it's already in kelvins, so we can just substitute them in. And we get a value of 0.31. We then repeat this process for the other 3 values as shown. And this is the second one. And this is the last one. Now notice we've got 0.31 and the rest is 0.32, but that's actually okay. That's acceptable because you could still argue to 1 decimal place, which you could because you could round all of these to 1 decimal place. You're still getting 0.3 as a constant value. And because they're all roughly about 0.3, we can say that dividing pressure by temperature gives us a constant. So therefore, pressure and temperature are proportional to each other. And that's how you use the data to show a proportionality relationship, just like with Charles's law.